Hello everyone, welcome to the channel. In this video, we will see one-dimensional step bar of finite element analysis. The problem states that using direct stiffness method, determine the nodal displacements and stresses of the stepped bar as shown in the figure. Take E equal to 210 gigapascal for bar element. So here E is Young's modulus. So how do you solve this problem? So the very first step is step 1. We have to divide this domain into element. Divide the domain into elements. Okay, so now here elements means element will have ends, and these ends are called as are nodes. Okay, so now we have to divide the domain into elements. So there is a rules also to divide the domain into elements. So what are the rules? The first rule states that change in shape, whenever we have a change in shape or geometry, we have to divide the domain into element. So if you see, so we have a diameter 60 and we have a diameter 40. Okay, so here there is a change in shape, so we are going to divide this into an element. Okay, we are going to divide this into an element. Okay, now there is one more rule, change in load. So whenever we have a change in load in our problem, so again we have to divide. So if you see, this 20 kilonewton is not applying in on the node, right? It is applied in the element. Okay, so in the 60 diameter element. So again, so here also there is a change, so it will be also divided. So if you see this three things, so we have almost three element. Okay, so we can start it from here. So this is first element. So the dimension for this element is 150 mm, and from here again we have a second element. Dimension for this is 50 mm, and from this node we have again the last element, that is the third element. The dimension for this is 150 mm. Okay, so now, so this first node as a fixed end, so we have to give the numbering as well. So this is our first node, second node, third node, and fourth node. So this is our first element. To differentiate, I'm just making it a square or rectangle. This is our second element. This is our third element. So total element we have 3 and total node we have 4. So elements equal to 3 and nodes are 4. Okay, so if you see, element 1 is lying between node 1 and 2. Okay, so if you see, element 1 is between 1 and 2. Element 2 is between 2 and 3. So element 3 is between 3 and 4. So these are the table sort of. Element 1 is between 1 and 2, 2 is between 2 and 3, 3 is between 3 and 4. Okay, so now we have divided the domain into element. Now we have to go to the second step. We have to write the formula, that is the element matrix equation. So in short form we can call it as EME. So this is for individual element. This formula is for the individual element. So in general we can write it like this way. K into U in equal to load. So this K is nothing but the stiffness matrix. It's nothing but stiffness matrix, and this U is a displacement vector. So displacement vectors. Vector is nothing but a single quantity, or else we can say it's a scalar one. Single as in it will be a column vector, column matrix, or this can be called as primary variable. Primary variable. So this is called as a force vector or load vector. So this is P is nothing but force or else load vector. So again, this is a column matrix which contains load values. So this can be called as secondary variable. Secondary variable. Okay. So this is generalized formula. Now the actual formula is for stiffness matrix, it will be A E divided by L small l into 1 minus 1 minus 1 1 into displacement u1 u2. This will be equal to load, that is P1 and P2. Okay, so now we have to find all the parameters for element wise. So step 3, element number 1. So in element number 1, we know the length L1 equal to 150 mm and the diameter was 60 mm, and the Young's modulus they have taken as E, they have given as E equal to 210 gigapascal. So again we have to convert this into a Newton per mm square, because gigapascal is 10 power 9 pascal. So 1 pascal equal to 1 Newton per meter square. So you have to convert into millimeter square. So if you do that, it will be 210 into 10 power 9 into 1 by 10 power 6 into Newton per millimeter square. So this get cancelled. We will have 210 into 10 power 3. So Newton per millimeter square. Okay. Now we have to find the parameter, that is A1. This is our first element. So I'm just writing suffix A1, U1, L1. So A is area pi by 4. The diameter for this is 60 square. Okay, so into E1 is the same Young's modulus 210 into 10 power 3, and the L1 is 150 mm. So if you do it, if you put it in the calculator, we'll get the value as 3.9584 into 10 power 6 Newton per mm. Okay, and now I'll just put it in the equation as well. So it is 3.9584 into 10 power 6 into 1 minus 1 minus 1 1. Here we'll have u1 u2. This will be equal to P1 and P2. So I'll just multiply this inside. So 10 power 6 will be at outside. So 3.9584 minus 3.9584 minus 3.9584, 3.9584 into u1 u2. This will be equal to P1 P2. Since it is a first element, it is our first element. If you go up, the first element is lying between node 1 and 2. So it's necessary to write down the numbers over here. The numbers are 1, 2, 1 and 2. So why we are writing this number, it will be useful in future steps. Okay, see. So now element 2, In similar manner, we have to find out for the element 2 as well, element number 2. So for element number 2, we have L2, it is 50 mm, and what else we have? The diameter. Okay, here the diameter will be same. Okay, so the L will be changing, it is 50 mm, but the diameter will be same because it was of the first element only, so the diameter will be same. So diameter will be D will be equal to 60 mm, and similarly E2 will be equal to same 210 into 10 power 3 Newton per mm square. So find out the values, that is A2 E2 divided by L2. So we'll get pi by 4 into 60 square into 210 into 10 power 3 divided by 50. So this gives me the value of 11.875 into 10 power 6 10 per mm. So again, in the similar manner, I'm going to write down the same thing. I'm going to put it in the matrix form. So 11.875 into 10 power 6, 1 minus 1 minus 1, 1. This will be into here. The element 2 is lying between 2 and 3. If you see, the element 2 is lying between 2 and 3. So here the numbering will be for U will be, it will be U2 and U3. And this equals to P2 and P3. So here we'll have the suffix at 2 and 3 because we are dealing with second element. So the second element node is 1, 2 and 3. So now I'll multiply it. So 10 power 6 will be at outside the matrix box. 11.875 minus 11.875 minus 11.875 and 11.875. So again it will be U2, U3. This will be equal to P2 and P3. So as we saw, the element 2 is lying between 2 and 3. So numbering will be 2, 3, 2, 3. Now the last element, that is element number 3. Element number 3. So here element 3, that is L3, will be equal to 150 mm, and the diameter it was 40 mm, 40 mm, and E3, that is Young's modulus for this particular element, is again same 210 into 10 power 3 Newton per mm square. So find the values A3, E3 divided by L3. Here we'll have pi by 4 into 40 the whole square into 210 into 10 power 3 divided by 150. So if I put it in the calculator, so this gives me 1.7593 into 10 power 6 Newton per mm. Okay, so again 1.7593 into 10 power 6, here 1 minus 1 minus 1, 1. So now it is third element. So third element is lying between 3 and 4. So here U3 and U4. This gives me, so this equals to P3 and P4. Okay, so again I'll multiply inside 10 power 6, 1.7593 minus 1.7593 minus 1.7593, 1.7593. So this into U3, U4, this gives equal to P3 and P4. So now the numbering is between 3 and 4. So 3 and 4. So because the third element is lying between 3 and 4. So third element is between 3 and 4. Okay. So we have calculated all the element wise calculation. Now we have to do the fourth step, that is the assembly of the stiffness matrix. step 4, assembly. So in assembly of elementary matrix equation, EME. So we have to assemble all the matrices which you found out using element matrix equation. So if you know, see, so here total nodes equal to 4. So the assembly matrix will be equal to 4 into 4. So number of nodes will be equal to the number of rows and columns for the assembly matrix. Okay, so this is one thing we have to remember. So if we have three number of nodes, so the matrix will be 3 by 3. If it is two number of nodes, then the matrix will be 2 by 4. Okay, so how do we assemble it now? If you see in entire thing, the entire element matrix equation, we have 10 power 6 as common, 10 power 6, 10 power 6 and 10 power 6. Okay, so we will be keeping the 10 power 6 outside the matrix. So 10 power 6. So the matrix we will have 4 by 4, 1, 2, 3 and 4. So here also 1, 2, 3 and 4. I'll just make a line so that it will be easier. Okay, so now again here we will have u1, u2, u3 and u4. So this is equal to p1, p2, p3 and p4. Okay, so now how do you fill these blocks? Now how do you fill these boxes? It's very simple. So first start with the first row. This is our first row, first column. Okay, first row, first column. Again we have to look for the numbering which we have used in the element matrix equation. If you see, this is our first row and this is our first column. The place is 3.9584, 3.9584. So here 3.59, sorry, 3.9584, 3.9584. And again first row, we have to complete this row, entire row, first row, second column now. So first row, second column. So first row, second column, this is minus the value of the first one. So minus 3.5984. Okay, so we have to check for 1 comma 3. So there is no 1 3. Okay, so 3 and 4 will become 0. We don't have any value, so it will become 0 0. So now second row, 2 comma 1. So second row, first column. So second row, first column is this value, minus 9584, minus 3.9584. So now second column, second row. Okay, so if you see the table, we have 2 as common node, right? This 2 as common node. So the 2 is coming from element number 1. Again, the 2 is coming from the element number 2. So we have to add these elements. Okay, so there will be a common node in element number 1 and element 2. So we have to add these values. Similarly for over here as well. So we have common node as 3 and 3. Again, we have to add these values. So as of now we have 2 comma 2. So there will be 2 comma 2 in 2's element number 1 and element number 2. So if you see, so we have this value 3.9584 and here also we have a 2 comma 2. So 11.875. So we have to add these values. Okay, so if you add these values, we get the value as 15.833. Okay, so here we have to add this value. I'll write it down. 3.9584 plus 11.875. So this gives me value as 15.833. So now 2 comma 3. So 2 comma 3 is minus of 11.875. minus of 11.875. So 2 comma 4 is, there is no 2 comma 4, it will become 0. So now 3 comma 1, since we didn't have 1 comma 3, again 3 comma 1 will become 0. So we have to go for 3 comma 2. So 3 comma 2 is minus 11.875 minus 11.875, and again we have a 3 comma 3 over here. So 3 comma 3 11.875, here also 1.7953. So when you add this both, we'll get the values as 13.634. And similarly 3 comma 4 is nothing but minus 1.7593 minus 1.7593. So 4 comma 1 is 0, 4 comma 2 is 0. So now 4 comma 3 and 4 comma 4. So these are the two values we are left out with. So minus of 1.7593 and plus 1.7593. Okay. So you are done with the stiffness matrix, assembly of the matrix. Okay, so that is, so this is the stiffness matrix. This is the stiffness matrix. So there is a method to check the stiffness matrix. What we did is right or wrong. Okay, so how can we check it? That the properties say that the very first property say that the diagonal of the matrix should be 0 or else positive value. Diagonal of the matrix should be 0 or positive value. If you see, so this is plus 3.9 plus 15 plus 13 and plus 1.7. Okay, so the diagonal is plus, so the all the values are positive. Okay, the second one is it is a square matrix. Exactly, so we have 1 2 3 4 1 2 3 4, so it is a square matrix and it's a symmetric matrix. The third one is that if you add all the elements of first row, if you add all the elements of the row, it should be equal to 0. So you can check it out. See, so 3 plus 3.958 and minus 3.95, so it is equal to 0. The second row, you can, if you add this minus 3.958 and minus 11.8 will give you 15.833, and similarly for the third and similarly for the fourth. So all the element of the row, the addition of all element of the row will be equal to 0. So these are the methods, these are the steps you can use to find whether your stiffness matrix, your assembly is right or wrong. Okay, now we did the assembly. The second step, the fifth step is, step 5 is apply boundary condition. Apply boundary condition. Apply boundary condition. Okay, so here for the boundary condition we have to check for the figure diagram. Okay, so in this is your u1, u2, u3 and u4. So if you see, u1 is fixed, so this node is fixed, that means it is not going to move anywhere. That means u1 will become 0. So u2 we have to find out, because we have applied, that is a load is applied, so we have to find out at by how much mm the u2, u3, u4 has been moved. That is a displacement. So we have to find out u2, u3 and u4. Okay, now for the displacement part, we know that u1 is 0 because it is fixed. So u2, u3 and u4 we have to find out. Now go for the load vector. So if you see, the same thing here, we'll have a P1, P2, P3 and P4. So the P1 is fixed. P1 is fixed, this means that there will be some reaction. Okay, there will be some reaction. So there will be some reaction, we have to find out. And at P2 we have a load, it is 20 kilonewton. And at P3 there is no load, and third node we don't have any load, it will become 0. And P4 we have a 15 kilonewton. So both are in the positive direction, that is they are moving from left to right. Okay, so P1 we have to find out. We have to find P1. The P1 will be equal to question mark. P2 equal to 20 kilonewton, that is 20 to 10 power 3 Newton. And P3 equal to 0. And P4 equal to 15 kilonewton to 10 power 3. So now we have to put all these values over here. So I'll just use the same thing. So this will become 0. So P1 we have to find out. So P2 will become 20 into 10 power 3. So P3 will become 0 and P4 will become 15 into 10 power 3. So these are the values we got. Now we have to frame the equation. Okay. So how we want to frame is that, so the first element of the stiffness matrix will be multiplied with the first element of the displacement matrix. The second element of the second column and first row of the stiffness matrix multiply with the u2. So that means this multiplied with this. Okay, so we'll see. First we'll frame a equation. So step 6, framing equation. So here, so if you multiply this with 0, you'll get 0. Now minus 3.958 into u2 minus 3.9584 u2, and we had 10 power 6 as outside, so it will become 10 power 6 equal to the other two columns, other two values are 0. So if you multiply with this 0, 0, 0, this is equal to the first row, that is P1. This is equal to P1. Now similarly go to the second row again. So second row, first element will be multiplied with the first one, second will be second, third will be third, and so on. So if you multiplied, we have these two values, this and this, because the last one is a 0, 1. So 15.833 u2 into 10 power 6 minus of 11.875 u3 into 10 power 6. So this is equal to 20 into 10 power 3, because here we have P2. Okay, now the third one, so in third one, the first one is 0, we have all other 3 as well. Okay, so into multiply by u2, u3. So in the third one, we'll have the equation as minus 11.875 u2 into 10 power 6 plus 13.634 u3 into 10 power 6 and minus 1.7593 into u4 into 10 power 6. So this is equal to P3 is 0. And similarly the last one, if you see, we have 0, 0, so this will go 0 and 0. We have this 2, so this will be multiplied with u3 and u4. So minus of 1.7593. So minus 1.7593 u3 into 10 power 6, then plus 157593 u4 into 10 power 6. So this is equal to P4. The P4 value is 15 into 10 power 3. Okay, so we have to take this equation, take this equation, take this equation. So here we have 3 unknowns. Okay, 3 equations and 3 unknowns. So you have to put it in the calculators. For this 3 equation and 3 unknowns, we will get the values of u3, u4, sorry, we'll get the values of u3, and again you will have a u2 as well. So we have the values of u2, u3 and u4. So if you put it in the calculator, we'll get the values as 8.843 into 10 power minus 3 mm of u2, and u3 is 1.0107 into 10 power minus 2 mm, because these are displacement, so the unit will be mm. So the last one, u4, is 1.8633 into 10 power minus 2 mm. So these are the required nodal displacement of the given step bar. Okay, now we have to find the value of P1 as well. So we know the equation of P1. Here this is the equation of P1. We have to substitute the value of u2, and we'll get the P1 as, if you put in the calculator, we'll get the value for P1 equal to minus 3.9584 U2 into 10 power 6. If you put the value, you will get the value as minus 35 into 10 power 3 Newton. So if you see, we will take the summation of P, we'll have P1 plus P2 plus P3 plus P4. So this should be equal to 0. Okay. If you see, we got P1 as minus 35 and P2 is 20. So here they have taken 10 power 3, I'm converting to kilonewton as well, plus P3 is 0 plus 15. So it is equal to 0. That means the value, the nodal displacement we got, it is correct. Okay. So here again, so all the values are positive. P2 and P3 were positive, and on the fixed end we'll have a negative value because it is a reaction. Okay. So by this method also we have corrected the values. Now the second question is you have to find the stresses, right? Calculation of stresses. So it is very simple. The formula for calculation of stresses is stress for the element equal to strain of the element into Young's modulus. So this element stands for the element, how many elements we have. If you see, we have three elements. We have three elements. So 1, 2, 3. So we have three stresses. So the stresses will be of 3. So it depends upon the element. So for element number 1, so this will be stress for 1. This is equal to strain is equal to 1 by L1 into minus 1. This will be into U1 U2 because the first element, so displacement will be U1 and U2 into E. So E can be here also, we'll put it. So this can be E is 210 into 10 power 3, L1 is 150. This will be multiplied with this thing. The first one will be multiplied with this one, and second one will be multiplied with this one. So minus of U1 plus U2. Okay, so we know that U1 is a fixed one, so it will become 0. And if you put the value of U2 we got it as 2 into 10 power, so 210 10 power 3 150 minus 0 plus U2 we got it as 8.843 into 10 power minus 3. If you do the calculation, we'll get the stress for the first element equal to 12.38 Newton per mm square, which is a tensile one. It's a positive value, it's a tensile one. Now for the element 2, element number 2, stress will be again E divided by L2 into minus 1. The second element lying between 2 and 3. Okay. So here this will be 210 into 10 power 3. Second element, the length is 50 minus 1. So again it will multiply like this here. So I'll write it down U2 plus U3. So if you put the values of U2 and U3, we'll get the value for stress for 2 is 5.3088 Newton per mm square. Even this is also tensile stress. Okay, because the value is positive. Now for the third element number 3, so this will be stress equal to E into L3 minus 1. Third element is lying between U3 and 4. Okay, so this will be E is 210 into 10 power 3, L3 is 150 into minus U3 plus U4. We'll put the value, we'll get the stress 3 equal to 1 point, so not 1 point, is 11.936 Newton per mm square. So these are the stresses of the element we got. So we have found the nodal displacement and stresses of the stepped bar. I hope you understood this problem very well. If you have any doubt, you can put it in the comment section. Thank you for watching.